Okay, so two more properties that I want to make sure we talk about in this packet are the product and quotient properties of radicals. And those are relatively easy, pretty self-explanatory, but I want to make sure that we cover them before we move forward. The product property, if you have the nth root of a times b and you separate them into two terms, you can actually separate your a completely from your b by keeping them both within the nth roots of your original problem. So looking at your quotient property, we can do the same thing here. If you have the nth root of a divided by b, we can take the nth root of a divided by the nth root of b. We can separate the two of them. And what this does is it helps us simplify things a little bit quicker when we can look at them as separate values and separate numbers. Or by combining them into bigger numbers, sometimes that helps us too as well. So let's look at example 6. In example 6, letter A, we're looking at the cube root of 3 times the cube root of 9. Now both of them on their own, we can't take the cube root of 3 and we can't take the cube root of 9. But we could look at them by multiplying them together and see if we then could take the cube root of that answer. So if we do that, 3 times 9, so we keep our cube root. 3 times 9 is 27, so 27 stays inside of our radical. And since we have 27, we know that 3 times 3 times 3 is 27. That the cube root, we need 3 of those 3's inside to be able to pull them out, which we do. So the cube root of 27 is 3. Same thing for letter B. In letter B, we have the 4th root of 48 divided by the 4th root of 3. In this situation, we can't take the 4th root of either of them individually, but if we combine them together, 48 divided by 3, 48 divided by 3 inside our radical is 16. And since there is a number multiplied by itself 4 times that gives us 16, we know the 4th root of 16 is 2. Couple quick things is we have an index over here that is odd. We have an inside number that's positive, so we know we have one solution. Here we have a 4th root, so we have our index that is even, an inside number that's positive, so we know we have 2 answers to this guy. Okay, so flipping it over, we're going to look at simplifying radicals and how these properties can come into play in a different situation. Okay, so simplifying radicals with index n in simplest form is when there are no perfect nth powers in the radicand and there are no radicals in any denominators. I'm just reading from the table up above. So basically what that means is simplest form means I can't take anything else, no other perfect nth powers out of that original value. So looking here, we've got the cube root, example 7, cube root of 40. In this case, I want to separate 40 just like I did, like if we go back and we look at the square root of 20, we can separate this into 2 square roots, right? One of them, which is a perfect square, square root of 4 is 2, so we can simplify square root of 20 into 2 square root of 5. We're kind of keeping that same concept, except we're getting away from just square roots. We're looking at what happens when we have radicals that have higher indexes than just 2. So in this case, I'm looking at 40. I know I want to pull a perfect cube if I can out of the 40, which means I have to know my perfect cubes, right? So 1 cubed we know is 1, 2 cubed we know is 8, 3 cubed we know is 27, 4 cubed we know is 64. So we want to see if we can pull any of these numbers in this column, the 1, 8, 27, 64, and so on, out of 40, which we can because 8 goes into 40. And we can separate this by taking the cube root of 8 times 5, right, because 8 times 5 gives us 40, and then we can separate this by both values, so cube root of 8 times the cube root of 5. And we know the cube root of 8 is 2. And the cube root of 5, we don't have, 5 is not a perfect cube, so we can't do anything about that. So our final answer is 2 cube root of 5. So we're doing the same thing we did before with our square roots. The only difference is we're looking at indexes of 3 or 4 or much higher. So we need to kind of, I guess, go back and remind ourselves of what those perfect cube roots are, perfect squares, perfect cubes, perfect fourth powers, so on and so forth. In letter D, we're going to look at this a little bit differently. We have 1 over 8. Obviously, there's nothing that we can do here in terms of simplifying it. So we're going to use our other property, our quotient property, and we're going to separate our numerator from our denominator. So here we've got the 4th root of 1 over the 4th root of 8. Okay, so again, our index is 4, which means we have to have 4 of the same number inside my radical in order to be able to pull out a perfect number. Okay, so in this case, we know that 8 can be broken down into 3 2's, right? But we're missing another 2 somewhere that would allow us to have 4 2's to be able to pull out of an index of 4. Okay, because we have here a fraction where we can't keep a radical in our denominator. So we have to see if we can change this or do something to this denominator to get 4 numbers to be able to pull out of an index of 4. Okay, so in this case, since we're missing 1 of the 2's, we have 3 of the 2's inside of the 8, right? Because 2 times 2 is 4, 4 times 2 is 8. So we can break the 8 down into 3 2's, but we're missing 1 more that would allow us to pull that number 2 out of the 4th root with an index of 4. So if we look at it this way, we still have to keep the same index, but now since we're missing 1 of the 2's down here, we can put that 2 in our second denominator over here on the right, so that we can multiply top and bottom by the piece of the denominator that's missing from this original 4th root. Okay, so we're missing a 2, so we're going to put the 2 here. We're going to multiply top and bottom by what our denominator is missing to allow us to be able to pull a perfect number, a whole number, out of our 4th root. So if we multiply up top, 4th root of 1 times the 4th root of 2 is obviously the same thing as the 1 times the 2 on the inside, so that's the same thing as the 4th root of 2, all over, well, 8 times 2 is 16, so again, this is the 4th root of 16, and since it's the 4th root of 16 now, 2 times 2 times 2 times 2, which gives us 4 times 4, which is 16. The 4th root of 16 is a perfect whole number, which is 2. We still have the 4th root of 2 up top, so our final answer is the 4th root of 2 divided by 2. Because now, in this case, we don't have a radical in our denominator anymore, which is what we wanted.